Okay, let's talk about 5.1. It's not going to be any homework out of 5.1, but 5.1 introduces the material of this next chapter. So we start by looking at two interconnected tanks. We've looked at mixing problems in the past, but in our previous mixing problems, we had one tank and we had something flowing into that tank and something flowing out of that tank. But here we have two tanks, and the two tanks are connected. Something is going into the first tank and something is coming out of the second tank. So we have 6 liters per minute of water, and something is going out of the second tank at a rate of 6 liters per minute. That's going to maintain a constant rate, a constant volume in these two tanks combined. So in the first tank, tank A, its concentration is going to be called X sub T, and in tank B, the concentration there is going to be called Y of T. Each tank has 24 liters in it. The concentration at the beginning for the first tank, we're just going to call X sub 0 kilograms, and the concentration at the beginning for the second tank, we're going to call Y sub 0 kilograms. So we have 8 liters per minute going out here, and we have 2 liters per minute coming this way. So notice we have 6 going in here, 2 coming in, so we have a total of 8 liters per minute coming in, 8 liters per minute going out. So this tank is maintaining a constant volume. We have 8 coming into this tank, 6 liters, 2 liters going out, so 8 total going out per minute. So this tank is maintaining a constant rate. So the concentration of the first tank is X kilograms per 24 liters. So X stands for how many kilograms of the solution are in there at a given time. The concentration of this one is Y kilograms per 24 liters. So if we want to know how the concentration is changing, this is the concentration, and we multiply it times liters per minute. Liters cancel, so this tells us the rate at which the concentration is changing. So that's kilograms per minute. So that's a change of mass per unit time. So that's a dx dt. So remember from previous studies that dx dt or dy dt is the input minus the output. So let's take these tank by tank. So for the first tank, this is pure water coming in, and this is a salt solution. Then pure water has no salt at all. So this inlet provides no change in salt. No additional salt added to it, no salt taken away from it. This one at the bottom, the concentration, this is coming from this tank, so this concentration is YT over 24, and then the volume change is 2 liters per minute. This is 24 liters, this is kilograms. So notice again, liters and liters cancel. So Y times 2 over 24, this is kilograms per minute. So that's how, that's the rate at which salt is coming into this tank. If we know the value of Y at a given time, we can find out how fast salt is coming into this tank. So that's the input. The output of that tank, this from here, this is based on what the concentration in this tank is. So that's X, the amount of salt divided by the volume, times how fast it's leaving. It's leaving at 8 liters per minute. So this is liters, so liters cancel. That's kilograms. So we're leaving at x times 8 over 24, and that's kilograms per minute. So if we simplify that, 2 and 24 reduce, so y over 12 minus 8 and 24 reduce, x over 3. So if you tell us the concentration of y at a given time and the concentration of x at a given time, or let me say that the mass of y at a given time and the mass of x at a given the same time, then we can tell how fast the mass is changing for this particular tank. So now let's look at the other tank. For the other tank, we have 3 pieces connected, and none of them are pure water. So coming into this tank, this is the input. So the substance that's coming in has a concentration of whatever the amount of salt in the first tank is over 24. So that gives us the concentration, and the rate at which it's entering into tank B is 8 liters per minute. So that lets us know how many kilograms per minute of salt are coming into this tank. Now for the output, we have 2 outputs. We have one here and one here. So out here, this is salt from tank B. So the concentration in tank B is y over 24. And through this port, it's leaving at 2 liters per minute. Going out of this one, it's the concentration from tank B times that's leaving at 6 liters per minute. So liters and liters. So how many kilograms per minute are leaving here? And I'll cancel those. How many kilograms per minute are leaving there? So if we simplify that, 8 goes into 24, so we have x over 3. 2 goes into 24, so y over 24, not y over 24, sorry. Let's do this. We have 2 over 24 and 6 over 24 here, so that's minus 8y over 24. So we have x over 3 minus y over 3. So that's our dy dt. We have a system here. Let's call this x prime equals y over 12 minus x over 3, and y prime equals x over 3 minus y over 3. Or if we want to put these in the same order, we can call this minus x over 3 plus y over 12 is the concentration or the rate at which the first is changing. The second one, x over 3 minus y over 12. So the rate at which x is changing is dependent on the amount of salt in each tank, and the rate at which y is changing is dependent on the concentration in each tank. So this one is actually not that difficult to solve. We can solve the second equation for x. So if we multiply through by 3, we have 3y prime equals x minus, if we multiply this by 3, we get y over 4. Sorry, I paused for a second because I realized that when I copy this down, this is supposed to be a 3 here. Y over 12 in the first one, y over 3 in this one. So if we multiply this equation through by 3, we get 3y prime on this side. If we multiply both of these by 3, the 3's cancel, leaving us x minus y. So if we add y to both sides, x is 3y prime plus y. So this is x. If we wanted x prime, we would have to take the derivative of this. Well, the derivative of the first derivative is the second derivative. The derivative of y is y prime. Why did I do that? Because this top equation has x and x prime in it. If we replace x prime with 3y double prime plus y prime, and then if we replace x with 3y prime plus y, then this whole equation has just y's in it. This equation no longer has y's and x's. It just has y's, the first derivative of y, and the second derivative of y. So let's do a little work here. If we divide each of these by 3, 3y prime over 3, the 3's would cancel, leaving us minus y prime, minus y over 3, or we could call that 1/3 y, plus y over 12, or we could call that 1/12 y. So those are like terms. So we have 1/12 minus 1/3, common denominator. That would make that 4/12. So that's minus 3/12 or minus 1/4. So that's how many y's that is. That's minus 1/4 y. So if we get all of our y's on the same side, we would add y prime to both sides. So we would have 3y double prime, 2y primes. Add that to the other side, we'd have 1/4 y equals 0. So this is homogeneous. If you don't like having a fraction in here, we could multiply everything by 4, and that would give us 12 y double prime plus 8 y prime plus y equals 0. So that differential equation describes our system in terms of y. And this is just second order homogeneous. So we could write our characteristic equation, 12r squared plus 8r plus 1 equals 0. That would factor to 6r plus 1 times 2r plus 1 equals 0. So r would be negative 1/6 and r would be negative 1/2. So y would be c1 e to the negative 1/6 t plus c2 e to the negative 1/2 t. So that would be y. And since we have a relationship between x and y, namely this, then we could get x. Remember, x is 3y prime plus y. So to get x, we need to know what y prime is. So if we take the first derivative of y, then the derivative of e to the u is e to the u times u prime. So the derivative of the exponent is negative 1/6. So negative 1/6 c1 e to the negative 1/6 t. The derivative of this is e to the u times u prime. The derivative of the exponent is negative 1/2. So I guess we could erase that plus and just have it as a minus. So that makes x 3 times negative 1/6 c1 e to the negative 1/6 t minus 1/2 c2 e to the negative 1/2 t plus y. So plus c1 e to the negative 1/6 t plus c2 e to the negative 1/2 t. So we have a negative 1/2 c1 e to the negative 1/6 t, and we have a 1 C1 e to the negative 1 6t. So 1 minus 1 half will make that a 1 half. We have a minus 3 halves C2 e to the negative 1 half t. And we have a plus 1 C2 e to the negative 1 half t. So minus 3 halves minus or plus 1 will make that a minus 1 half C2 e to the negative 1 half t. So that's our x. It gives us an equation for y and an equation. So let me copy that down. The y went down. So y is C1 e to the negative 1 6t plus C2 e to the negative 1 half t. So what else do we know? We know that at time 0, if we put a 0 in for our time, that 0, so we would get a 1 half C1 because e to the 0 is 1. If we put a 0 in for t here, that's 0, so that's 1, so minus 1 half C2. And we call the salinity at time 0 for x sub 0. Same thing for y as time 0. At the beginning, if we put a 0 in, we get 1 C1 plus 1 C2, and the amount of salt at the beginning we call y sub 0. So that's the salt in the second tank. That's just a system of equations in terms of C1 and C2. X sub 0, y sub 0, those are given values, our initial values. So we can solve this system of equations several different ways. If we double that top equation, we would get C1 minus C2 is 2x sub 0. If we add these two together, we would get 2 C1s. Those would cancel. We would get 2x sub 0 plus y sub 0. If we divide by 2, C1 is 2x sub 0 plus y sub 0 over 2. If we, let's see, if we multiply that top equation by negative 2, then we would have minus C1 plus C2 equals negative 2x sub 0. Bring down the second equation. When we add those equations together, the C1s cancel, so 2 C2s is y sub 0 minus 2x sub 0. So C2 is y minus 2x over 2. Once we have C1 and C2, we can substitute those in, and we can write our solutions. So let's copy this over. And let's go back and copy C2. Put that. Let's put that on this page. So I guess we can finish this. So x is 1 half times C1. Well, if we multiply this times 1 half, we would have a 1/4 on, or a 4 on bottom. So 2x naught plus y naught over 4 e to the negative 1 6t minus, if we multiply this times 1 half, we'll have y naught minus 2x naught over 4. And if we're multiplying that by 1 half, that's C2, so e to the negative 1 half t. We could distribute that negative in there and make that a plus, that a negative, and that a plus if we wanted to. And then for y, if we put that in for C1, this one doesn't have the 1/2 times it, so 2x plus y over 2 e to the negative 1/6t plus C2 y minus 2x over 2 e to the negative 1/2 t. So those two equations, those two functions of t, notice both of those are functions of t. They tell us how much salt will be in each tank at different times. The only thing we have to know is how much salt did we start with in tank A, how much salt did we start with in tank B. Notice as time increases, as t gets bigger and bigger, then this is going to get smaller and smaller. Since that's a negative, that's really 1 over e to the 1/6 t and 1 over e to the 1/2 t. So as t gets bigger and bigger, this is getting smaller and smaller. Why is that? Because we're adding pure water into our system, and we're taking out salt water. So over time, our concentration is going to get weaker and weaker and weaker. The amount of salt is going to get lower and lower because we're pulling salt out, but we're not putting any back in. So over time, we're losing salt here, we're losing salt here because it's going out this exit. So that is that's kind of an introduction to what this chapter deals with. It deals with when we have systems of differential equations. We had two different variables, two different independent variables, or I guess you say dependent variables, x and y, with our independent variable being t. Two different differential equations, one involving x prime, one involving y prime. So we're going to look at how to deal with these more generically as we progress throughout this chapter.